Today we're going to look at the history of RF microwave components and find out how we went from vacuum tubes to modern microwave components.
We're going to be covering a lot of technical content for RF microwave design, from initial design in microwave office and 3D EM simulation to schematic capture and layout and measurements in the lab, with the penultimate goal of showcasing capabilities and doing business. And for that reason, I thought the best way to start the first video is to look at the history of RF microwave technology and start from the science and go into the engineering and into the modern era. I think you'll find this one interesting because rarely do you see folks integrating history and trends with physics-based explanation altogether at the same time. This is not a white paper or an academic paper, it's more of a opinion piece based on historical fact. Here I have a summary of historical developments using ChatGPT to put all the epochs into one graph. You can see how we started from the physics in the late 1700s and early 1800s and ended up with the physical layer, the physical infrastructure, all the way up to the digital networking, which is where we are for a lot of the cellular, Wi-Fi, and communication. So starting with at the very beginning, we have Orsted, which contributed to the field by finding out during a lecture that current being carried through a wire deflects a compass. And so what he did was he was able to relate electric fields to magnetic fields, because up to that point they were looked at as separate phenomena. With Faraday in 1831, he discovered electromagnetic induction, and again, what the theme at this time is integration of more and more phenomena that were thought to be separate from each other previously. So with EM induction, he was able to show that a changing magnetic field produces an electric field, and this is used to this day significantly for electric generators, induction motors, and the like. In 1845, he discovered birefringence, and people call this Faraday effect, and it's essentially that it proved that light and electromagnetic waves are connected. And once more, another integration of the forces together. What was thought to be separate from each other, they're actually related. So here he used magnetic fields along the same axis as propagation of light, and he was able to show that based on the strength of the magnetic field, polarization of light changes. And applications today are ferrite isolators, and they're very useful for actually what we do at Mobile Microwave, which is ruggedized power amplifier design. So you can see how something from the 1800s here affects us to this day. Of course, Maxwell's equations need no introduction, very famous. What Maxwell did was integrate again, once more, higher level integration of underlying observations from Coulomb, Orsted, and Ampere, as well as Faraday. He was able to integrate them all together and add a term called displacement current, which was revolutionary at his time. In 1873, he was able to complete his treatise on electromagnetic theory. The reason this is important is because the first time around, when he published his paper in 1864, he had 20 equations and 20 unknowns, and it was very difficult to solve those problems. And as you know, you're familiar with 4 vectorized equations, which Oliver Heaviside significantly contributed to shape the math into what it is that we know today. Maxwell also, in this treatise, formalized a lot of the concepts, added boundary conditions, energy storage in fields, and EM waves in various dielectric media. And so the way to really think about electromagnetics from then on is to consider that conductors guide electromagnetic fields, and that's an important development. Now, as for 1887, Hertz demonstrated that with a high voltage induction coil, you can produce sparks, and this electromagnetic wave travels, and if you tune your receiver, which is basically a spark gap, and you tune such that the resonance picks up the transmitted wave, he was able to prove electromagnetic generation, transmission through space, as well as reception. Next, we have in 1894 we have Oliver Lodge. So you can see the slow accumulation, slow evolution of electromagnetic theory and engineering. And with Oliver Lodge, you see that he basically uses Hertz's spark gap transmitter, but he uses coherers as a detector. And a coherer is basically a filament, and it's a conducting filament, and when the RF signal is present, these filaments get together and conduct electricity, acting like a diode essentially. And this began to demonstrate electromagnetic wave usage for communications and not just something you do in the lab for fun. In 1895, Marconi took this further again and repeated the same experiment by transmitting 1 to 2 kilometers over a hill. What he demonstrated is that electromagnetics is not just a line of sight phenomena. This was the first outdoor wireless telegraph, and he did a lot of tuning and optimization, which can be considered system engineering, for getting more power out and grounding the vertical antennas and being able to really transmit for a long distance. This is essentially the beginnings of telecommunications. In 1904, John Fleming invented the thermionic diode, and essentially this diode, this vacuum tube, uses thermionic emissions to rectify high frequency signals. It's essentially the birth of electronic detection using vacuum tubes. So moving away from the coherers and building something that's more robust, it's more reliable, and it helps with it initiates the beginnings of RF envelope detection. In 1906, we had the triode or the Audion, and it's essentially one more evolutionary step. By adding a third electrode to the Fleming diode, you now have a control grid in addition to the cathode and anode. And if you can see where I'm going with this, this is essentially a vacuum version of a transistor we know of today. So the third element essentially is like the gate or the base of modern transistors, and it modulated the electric field inside to where the speed of the electron flow was controlled, and you can get amplification out of that. In 1907, we had multi-grid tubes. The multi-grid solution essentially solves the vacuum version of the Miller effect due to the feedback capacitors between the plates. Now we have one of the giants of radio, which is Edwin Armstrong. In 1913, he invented the regenerative receiver, where he used positive feedback to increase gain and selectivity significantly. He used a triode and used part of the output to the input to be in phase with the RF, and he was able to use that feedback to eliminate the need for multiple tube stages to achieve gain, and he was able to really amplify weak and noisy signals. In 1917, he also made another significant contribution that exists to this day, which is the super heterodyne receiver, and this is extremely important as it relaxes filter design constraints as you reduce your RF frequency to an intermediate frequency, do your processing, and then convert back to RF. In 1933, he invented wideband FM, and this improved audio quality significantly over amplitude modulation due to less corruption by noise. And counterintuitively, he found that extending the bandwidth of the modulation index resulted in better noise immunity. Next we have in 1921 Albert Hall developing the magnetron principle, and essentially while he was at General Electric he used a vacuum tube with crossed electric and magnetic fields, and he was able to control the speed of electrons while they're in orbital motion by the strength of the magnetic field instead of control grids as we discussed previously. These crossed field tubes helped control electrons by fields and not electrodes. This also was the beginnings of geometry dependent frequency behavior, which we'll see more of. In 1924, the split anode magnetron by Eric Caban was invented, and this isolation of into two halves helped transform the magnetron principle from a rectifier tube to a self-resonant RF source. And this is a nonlinear self-organizing oscillator essentially, and it uses electron bunching physics. In 1929, slotted anode magnetron was developed, and essentially by adding more segments and using radial slots to separate them, a higher frequency of RF could be achieved and better RF confinement, and several modes, which are called multi-mode behavior, was observed, and higher power extraction could be achieved. In 1935, multi-cavity magnetrons were invented, and with multi-cavity magnetrons you added more control of how the electrons were oscillating between each spoke or each section, and so this enabled higher power microwave generation. And in 1940 we had the cavity magnetron, which is the penultimate magnetron used for radars and the microwave ovens that we know and use today. The cavity magnetron was capable of producing hundreds of watts in a centimeter wavelength, and it had a very high efficiency, and it was the first practical high power microwave source. It had a strong nonlinear interaction. The relationship between the electron velocity and the RF phase velocity determined how much energy you can pull out of the magnetron, and this was used in airborne radar, submarine detection, and aircraft interception. And it really became a military and industrial workhorse. In 1935, velocity modulation theory was developed by Agnesa and Oscar Heil, and it used electron bunching physics to develop linear beam tubes, and this enabled amplification at microwave frequencies. The idea was that instead of focusing on modulating the density of electrons as you would with a grid structure, you should focus on affecting or increasing the speed of the electrons, similar to the definition of current, where you can move a large number of charges per second across the surface or accelerate a fewer number of charges and still get the same current. And due to the limitation of grid control tubes at microwave frequencies due to transit time limitations, the beam bunching physics in velocity modulation theory enabled a new way of looking at how to accelerate charges and get gain out of microwave amplifiers. In 1937, the klystron was invented by Russell and Sigurd Varian and Hansen, and it's the first practical velocity modulated microwave amplifier. It is a linear amplifier, and when the beam velocity matches the cavity phase velocity, you have a strong interaction that leads to the amplification. In 1943, Rudolf Kampfner developed the traveling wave tube, during World War II, which is still in use today. And the idea is to use continuous interaction between an electron beam and the RF wave traveling in the long wave structure to increase bandwidth and gain. And so the physics-based idea is that when you take an electromagnetic wave from vacuum to this long structure, you're slowing it down below the speed of light. And since electrons have time to catch up, every time they travel through each part of the structure, they gain energy and you're able to produce a higher output RF power at the end of the physical structure. These are used for airborne radar, satellite communication, electronic warfare, and microwave relays. In 1950s, multi-cavity and reflex klystrons were two paths. The multi-cavity was for power scaling, essentially addition of more buncher cavities and spaces for drifting, and the reflex klystron was a compact oscillator with the addition of a repeller electrode. So essentially more engineering of the electrons in the cavities. Now moving on to radar systems. In 1938, the first operational radar was used in the UK. It was called the chain home radar. In the 1940s, we moved to pulse radar systems and duplexers. If you think of duplexers, they're essentially what protects the receiver from the transmit time of the radar. And at that time, it used to be gas discharge tubes, where the high power side would excite the gases and protect the input, whereas when the reflection came from the object, it would not excite that gas discharge tube, and so the receiver was protected. Today we would use Farad circulators, waveguide switches, or pin diode switches for achieving similar functions. For the pulse radar, it enabled higher peak power, which helps increase range and increased average selectivity. In the 1950s, Doppler radar was invented, and several labs worked on this. And it enabled, due to the Doppler effect, it enabled measuring range when it was pulsed. On top of range during pulsed measurement, it enabled the measurement of speed of objects and enabled better discrimination between different objects and stationary versus moving objects. In 1947, the transistor was invented by Bardeen, Brittain, and Shockley. I happen to have gone to the same school as Bardeen, so I'm always proud of that. University of Illinois, Urbana-Champaign. Proud to be an Illini. So this was the first point contact resistor, and several years later, Shockley went on to invent the bipolar junction transistor. In 1954, the silicon transistor radio was developed by Texas Instruments using germanium transistors. This was the first transistor radio, and so it required small batteries instead of high voltage power supplies. It was pocket sized, didn't require a warm up, and it was ruggedized. In 1966, gallium arsenide MESFETs were developed by Carver Mead, and due to the higher electron mobility of gallium arsenide, you get a higher transition frequency, which enables higher frequency operation. This semiconductor material is also direct band gap and has a higher saturation velocity. In the 1970s, gallium arsenide mimics were developed to better integrate microwave circuitry into single chips, compared to using hybrid module assemblies and wire bonds. It enabled better integration, which has been a trend in electronics for many decades. In The 1950s, printed microwave and integration was another um, trend, and again follows that same theme of integration and miniaturization, as well as enabling a planar, repeatable design with higher precision, etching away top of the material on a microstrip to design planar transmission lines. Microstrip operates based on quasi-TEM, EM wave propagation, and coplanar waveguide is actual TEM propagation and confines the fields better. That's why you see patch antennas designed in microstrip, because of the radiation effect from the field that is not very confined in quasi-TEM. In the 80s, touchstone and other computer-aided design methodologies were developed as microwave network design was becoming more popular, and S parameters were being used more and more to describe different microwave modules. And in the 70s and 80s, we can summarize by saying that cellular phones and GPS were being developed, and you can see in 1973 the first handheld giant cell phone by Motorola. And in 1978 we had GPS satellites based on DoD budgets and developments. In 1989 you had smaller pocket cell phones by Motorola, and in the 90s and 2000s you had the birth of modern digital wireless systems with GSM and IEEE 802.11, different digital based schemes to basically revolutionize radio from an analog type of communication mode to a network engineering problem. And so in 2001 we have the WCDMA. As we're getting closer to the end of the presentation, things are a lot more familiar to you all, and so I'm not going to spend a lot of time explaining what the network level implications are. But as far as RF and microwave goes, you can see how the field evolved over the years. You're familiar with LTE, 5G, and Wi-Fi 6 and 7. The idea is essentially that we move to digital communication, networking, packet-based data, spectrum efficiency, and being able to accommodate more and more users. That's the trend in this domain. And as far as the very end of this presentation goes, the focus is on solid-state high-power microwave, which is our focus. We do work on other peripheral RF microwave subjects and electronics, control loops, telemetry, but our core focus is design of GaN, LDMOS, and other high-power microwave technologies. And you can see that the gas FEMT was developed in the decade, as you can see, the 1990s. And of course our key focus, gallium nitride HEMTs, from the 2000s to present, as far as usable GaN technology goes. I hope you enjoyed the video. We'll discuss more technical concepts and more practical concepts